Okay, welcome to Chapter 5, Section 6, the Law of Cosines, something I'm sure many of you have looked at before. Very similar to Section 5, where you would draw your triangle, label things A, B, C, and then little a, little b, little c would be the opposite sides of each angle. And when we do that, we have these three versions of the rule that we can look at. The way I remember it, there's definitely a pattern to it, and I just remember that the side I'm trying to find, that angle also appears, and everything else involves the other two sides. So here, side A and angle A, side B, angle B, side C, angle C, all the middle stuff involves the other two sides. The other thing to know for this particular law is that you're going to use it when you see a side angle side situation. That's going to guarantee you one triangle, or you can use it for side, side, side. And this is kind of a special case where potentially could be 0 triangles that are formed. Most of the time, though, I'd say there's one triangle. Okay, our first question, I've already drawn a few things in here. It says solve for triangle ABC if you know that little a is 28, little b is 35, little c is 17. And for pictures like this, or for situations like this, you can actually get a fairly realistic picture if you think about how those three sides are going to come together. Up here, just a little reminder of what we talked about already. Side angle side, one triangle, side side side, 0 or 1, because this is a side 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 situation. I need to be kind of careful, and we want to start with the biggest angle, trying to find the biggest angle. Just saves you a little bit of hassle. There is something tricky that can happen if we don't do that sometimes. So if we look at our picture, the biggest angle is going to be opposite the biggest side. So we're going to set this up as solving for, in this case, angle B, which means little b is off by itself. So I get 35 squared equals, we can say 28 squared plus 17 squared minus 2 times 28 times 17 times the cosine of angle B. So that's just the setup, and then what I generally do is square everything or multiply everything out. So from this I would get 1225 equals 784 plus 17 squared is 289. 2 times 28 times 17 is 952, and that's times cosine of B. And then I'm just going to work my way until I have solved for angle B. First thing I'm going to do is take the 784 and the 289, subtract it from both sides. So in the end I'm going to go 1225 minus those two values. If I go through and I do that, I'm left with 152. So imagine these two things are now gone, then subtracted from 1225. And so the next step then would be to divide by that negative 952. So in the end, do a little shortcut here, I'm going to get 152 divided by 952 equals cosine of angle B. And then from there, it's going to be a fraction that's in between -1 and 1, which is what I want, because I'm going to have to use inverse cosine. If I do inverse cosine of that fraction, I'm going to be left with angle B equaling 99.19 degrees. So that's a good thing. It seems like things are making sense. A pretty big angle, which is what I would expect from the picture. And then to find angle A, I could go, to find angle A, I actually need to set up law of sines now. Because if I know, a different thing here, if I know this angle right there, now I can start setting up the ratios from law of sines. I could go back and do law of cosines multiple times, but let's be honest, this is a lot of algebra work, kind of a pain to set up. So if I have an easier way of doing this, I'm going to do that first. So we'll just kind of split up our work right here. So I can look at sine of 99.19. That was angle B, remember, over side B, which is 35. And that's going to equal sine of angle A over little a, which is 28. Do my cross multiplying and dividing, and I'm going to get angle A is about 52.16 degrees. Which would make sense. 28 is the middle side length, so angle A should be probably an angle that's in the middle. Then to find the final angle right here, I can just go 180 minus the other two angles. 180 minus 99.19 minus 52.16, and then I get 28.65 as my final answer here. So this is what I'm looking for. Maybe one more thing to add here. The reason I knew that I would get one triangle from the side situation, going right to the beginning, if you go back to geometry class, you learned that as long as you could add up two sides to the triangle and it was bigger than the third side, if you could do that with all the possibilities, you'd end up with a triangle. So 28 and 35, if I add those together, is bigger than 17. 28 plus 17 is bigger than 35. And 35 plus 17 is bigger than 28. If I can't do that, I'm not going to be able to find a single triangle here. And the other way I would know this is when I got to this part right here, and I'd use inverse cosine to get this answer. If I got an error at that point, I would also know that no triangles were possible. Okay, next part here, we're going to do two things here at once. I'm going to prove this next thing to you. You guys don't really need to copy this down, but we have a triangle area formula that's a little different than our typical formula. Our typical formula is area of a triangle is 1/2 times the base times the height. See if we can squeeze that in there. And so based on the picture that I drew you right there, we'd say that area equals 1/2 times C times H. C is like our base in this picture. And I'm going to try and prove that we can get this part of our area formula. So we're going to set this up a lot like our proof for the law of sines. If I were to look at this right triangle right here, I could say that sine of angle A equals H over B, and if I were to rearrange that, I would get H equals B times sine of angle A. And so this is now going to go back into this part of my formula over here. So I'd end up with 1/2 times a C times what H equals, which is B times sine of angle A. And if I were to take it and just rearrange the B and the A parts, B and C parts, I would get this part of the formula. If we just took this triangle and rotated it, I would come up with the other parts. So we're going to use that in a very simple proof here, or a simple question on our last example. So we have a regular nonagon. That is a polygon with 9 sides. All the sides should be the same, and that means all the interior angles are the same as well. And it's going to be inscribed, so it fits perfectly inside a circle with a radius of 10 inches. So I have a perfect nonagon and a perfect circle drawn right here. And to solve this one, I want you to think about the very center of the circle. And if I were just to connect two consecutive points of the nonagon, I'm going to end up with a triangle. And so we can use our triangle area formula here to figure a few things out. If I were to keep doing this, I'd end up with, I believe, 9 triangles. Okay, our job is going to be to find the area of one of these triangles and then just multiply that by 9. So according to our formula, we're going to have 1/2 times B times C. So that would be a side times a side of the triangle, And I know, let me get a different color here, I know that this has to be 10 and this has to be 10. So if I'm looking at this triangle, I could say that this is B, excuse me, this right here maybe is B, and this is C. I have 10 times 10. And then this would be the third part of the triangle, third side of the triangle. I'm talking about the angle in between right here. This would be angle A. So I need to think about what that angle is going to be right there. Well, all the way around the circle is 360 degrees, and I'm going to split that into 9 equal parts. 360 divided by 9 is 40, so this angle right in here is 40 degrees. So I'm going to be taking sine of 40 degrees. I go through and I solve that. That is 32.14 inches squared. And then to get my overall area of the entire polygon, or nonagon, I'm going to go 32.14 times 9, and I get a total area of 289.25 inches squared. There are your notes for section 6.